Now the number of geometrical isomers is equal to the number of possible pairs, and for this type of complex the number of possible pairs was just 2. So there are 2 geometrical isomers. So now next let's go to the number of optical isomers. Number of geometrical isomers are 2. Number of optical isomers, as I said, depends only upon the number of optically active pairs. There were no optically active pairs, means there can be no optical isomers. So the number of optical isomers is 0. Next we go to enantiomeric pairs. So fill in the details you already know. Number of enantiomeric pairs is the number of optical isomers divided by 2. 0 divided by 2, 0 divided by anything is 0. So the number of enantiomeric pairs is also 0. Next we go to the number of stereoisomers. Again fill in the details or you already know. So that is 2. This one is 0. Enantiomeric pairs is also 0. And the number of stereoisomers is equal to the number of optical isomers, which is equal to 0, plus the number of optically inactive pairs. So there were 2 pairs and both of them were optically inactive. So this is 0 plus 2, which is equal to 2. So the number of geometrical isomers for the complex MA4BC are 2, number of optical isomers are 0, enantiomeric pairs is 0, and the number of stereoisomers is 2. Now we come to the octahedral complexes of M, A3, B2, C type. In this also there are 3 types of ligands present, but one ligand is thrice, the other ligand is twice, and the other ligand is 1 time. So it still gives it an overall coordination number of 6. So let's see the possible pair. So this is the first possible pair. In this, A is trans to A is trans to B, and B is trans to C. So A is trans to A, the same ligand is trans to each other, so this is an optically inactive pair. Now let's go to the next possible pair. This is the next possible pair. In this, A is trans to C, B is trans to B, A is trans to A. In this case, A is trans to A as well as B is trans to B. So this is also optically inactive. So till now we had 2 geometrical isomers and both of them were optically inactive. This is the next possible pair. In this, A is trans to B, A is trans to C, A is trans to B. In this, the trans pair is getting repeated. So this is also optically inactive. So these were all of the 3 isomers possible or possible pairs in the type of the complex MA3B2C. So we have seen that none of them are optically active, all of them are optically inactive. So in the next slides we will do the calculation for the geometrical isomers, the optical isomers, the enantiomeric pairs and the stereoisomers. So now the number of geometrical isomers we know is equal to the number of possible pairs, and the number of possible pairs for this complex were just 3. So the number of geometrical isomers is also going to be 3. Now the number of optical isomers. So first of all we know the number of geometrical isomers is 3. So optical isomers. Optical isomers, as I said, depends upon the optically active pairs, and there were no optically active pairs for this complex. So the number of optical isomers is also going to be 0. Next we come to the number of enantiomeric pairs, and again number of geometrical isomers were 3. Number of optical isomers is 0, which makes the number of enantiomeric pairs also 0, because the number of enantiomeric pairs is optical isomers divided by 2. Next we come to the number of stereoisomers. So fill in the details you already know. Number of stereoisomers is equal to the number of optical isomers plus the number of optically inactive pairs. So the number of optical isomers is 0, and there were 3 optically inactive pairs. So the total number of stereoisomers is equal to 3. So the number of geometrical isomers for the complex MA3B2C type were 3. the number of optical isomers was 0, the number of enantiomeric pairs was 0, and the number of stereoisomers were 3.